One thing that every calculus student does is find the maximum and minimum of certain functions, and they learn all sorts of techniques on how to do that. And of course, not every function has a maximum. Functions can go off to infinity, like this graph is doing here as we get close to 0. Remember, functions could be crazy. Like, what if we had a function that was generated by a random number generator plotting points at random? Would that have a maximum? If it did, would you even know how to find it? But I come to you with good news, because if you have a function that's continuous and defined on a closed interval, then it will always be true that that function achieves a maximum and a minimum somewhere over that interval. This is called the extreme value theorem, and it's one of the most applicable theorems in all of math because it has to do with optimization, which is something we want to do in the real world all the time. It's important that we work with a closed interval. If we have an open interval, it's possible that as we get near one of the endpoints, the function could shoot off to infinity, and other things could happen on an open interval as well. All right, let's give a sketch of the proof. And so as a first step, let's show that our continuous function on a closed interval cannot go off to infinity. Let's show that it's bounded. And so how do we do that? Well, we're going to argue by contradiction. And so if it weren't bounded, that would mean there was some point whose y value was bigger than 10, some y value that was bigger than 20, some y value that was bigger than 30, and we could do this on and on and on. And what we would get is a sequence of points whose y values are going to be getting arbitrarily large. Now look at the sequence of inputs that give us that. Those inputs are bounded between the endpoints of our closed interval. And so those inputs have to have a convergent subsequence by the Bolzano-Weierstrass theorem. But now that subsequence of inputs, well, if we look at those outputs, it's impossible for those to converge to anything because those outputs are going up and up and up. They're going off to infinity. But now we have a continuous function. And if those inputs in our subsequence are converging somewhere, then their outputs should converge to f of whatever that limit was. This is a contradiction. And somewhere in there I use the fact that the interval was closed, and it's in saying that the limit of that subsequence is actually an input. And that's true because the limit of that subsequence will be somewhere in our closed interval that we're working with, and it could be one of the endpoints. That's why we need it to be closed. That's it for today's video. In the next video, I'll finish this proof and I'll explain how we can actually show, knowing that our function is bounded, what our candidate will be for the maximum and how we're going to show that this actually occurs. Also, it'll be interactive and I'll let you play along if you want to see the way that we did this in class.